So again, you're welcome to do your notes on paper or in OneNote, or you can sit and watch, whatever, works for you. So last time we had met, we had kind of given a little bit of a course overview and kind of give you an idea of where we're going in trigonometry. We're going to start further back even than that, though, to start the year. With a little bit of review from some concepts from our Algebra 2 course. So we'll start with the most basic algebraic definition that you see in high school, that is of a function. So the function is a set of ordered pairs. Where the inputs come from a set D, and the outputs come from a set R. Such that every member of D is paired with exactly one member of R. These sets D and R are referred to as the domain and the range. So there's some different ways that we've represented functions in the past. Let's go and take a look at a couple of those representations and how to tell if something's a function or not. So this is like all the way back to like first semester of last year, but that's okay. Want to make sure everybody's on the same page. And if we go back far enough, we'll eventually find that page, right? So one representation that we would have talked about was the mapping diagram. So in the mapping diagram, we draw like two circles, one for the domain and one representing the range. Then usually we draw some dots representing the members of those. I'm going to just name those generically like x1, x2, x3, and y1, y2, y3. So let's say we have, I don't know, something that looks like this. So the arrows are just indicating how the elements are paired together. So let's use our definition above to try to decide whether this is a function or not. So the first thing we need to check is that every member of X is paired. So if I go through and I look, okay, each member from the domain is is paired with something else. That's good. And then the second thing I need to make sure is that they're only going to one place, which they are. Do I care what's happening in the range? I do not. To determine if something is a function or not, I only really have to look in the domain. So I need to make sure everything is used, and those things that are used only are paired with one thing. Okay, let's look at another couple of examples to make sure we got it. So let's say we have this. Is this a function? No. Why not? Yeah, we have some of the domains that are not paired, right? What if I add in this arrow? Is this a function? Yes, right? All the x's are used, and they're only going to one location. Does it matter that some of them are going to the same location? No. Does it matter that some of the locations aren't used? Some of the y's? No. Everybody's still doing okay there? All right. One more and then we'll move on. How about this one? What's the matter with it? X1 is going to two different locations. Very good. So this is not currently a function. To fix it, what could we do? Like just delete one of those two arrows would be fine. Now it's a function. Cool. All right. We feel comfortable about mapping diagrams and picking out functions and not functions. Should be easy, right? Stuff you did last year. We probably got pretty good at it. Another representation we can have for a function is with a graph. Maybe we should use a better word than that. So let's say we ask, does the graph of y equals x squared plus 2 define a function, there should be no a there, just define y as a function of x. So don't let the wording there confuse you, right? Saying y as a function of x is just saying that y is the dependent variable and x is the independent variable, which is kind of like the standard assumption we'd make for something that we write as y equals x squared plus 2. Everybody's good with that? So what should we do to do this? Yeah, go ahead. Okay, and what good is that going to do?
Like on your calculator, it's easier, but you can look at like if an x has 2 y's or not.
Okay, so how about we sketch the graph? When that's almost equivalent to what you're doing, right? So let's think back to our Algebra 2 class. What kind of function is this? Anybody? Y equals x squared plus 2. These functions that look like this have a name, right? Okay, so it's quadratic. But the point of that is, what do we know the shape of all quadratic functions is? Parabola. So yes, you're just a step ahead of where I was trying to get to, but perfect. Everybody's good with that? How do I know it's quadratic? The x squared, right? That the x squared is the biggest degree term. We're okay? All right. So what's this parabola going to look like in this case? Is it going to open up or open down? Good, opening up. How do you know that? leading coefficient, exactly. If the leading coefficient is positive, I know the parabola opens up. If the leading coefficient was negative, I know it opened down. And what's the plus 2 doing? Yeah, just shifts it up 2 units. Does that matter in terms of us figuring out if it's a function or not? No. But it'll look something like this. Now that I have the graph, is it easy to tell if that's a function or not? Yeah. How can I tell? The vertical line test was what we used. Very good. So what the vertical line test says is if I can draw any vertical line that intersects the graph more than one time, then that could not represent a function. Here, though, any time I draw a vertical line is just going to hit the graph once. Everybody agree with that? So that guy is a function. What if we have a graph that looks like this? Is that a function? No. Why not? Yeah, you can draw a vertical line that intersects the graph 3 times. Does it matter that I could draw this vertical line that only hits it once? Does that matter? No. It's just any vertical line that intersects the graph more than once, that graph cannot represent a function. Right? So you only need one vertical line to make it fail. All of the vertical lines don't need to make it fail. Or all vertical lines don't need to intersect it more than once. Yes?
Can we draw the line?
Absolutely. Yeah, go ahead.
I got it. Thank you.
Yeah. And I will say, going forward, that if you can't see because of the light situations, you don't even have to ask. Just stand up and turn off the lights. I'll never be upset about that. You being able to see is critically important. So if that helps, please do that. Yeah, absolutely. Okay. Everybody feel good about picking out whether graphs are functions or not? Pretty easy, right? Is this all sounding familiar? I guess I should double check here. Okay. Then I'm going to keep scooting along. You guys remember talking about function notation before? When I say function notation, I mean like y equals f of x. Which is basically just saying that y is the value of f at x, right? Is kind of what that symbolically is implying. So like if you thought back to your mapping diagram, if this is x and this is y, and this is the map going from x to y is f, this basically means that y is the transformation of x under that function f, right? It's some procedure to turn it into this y. Okay. The nice thing about function notation is that it is very specific in telling us which ones are the independent and dependent variables, right? That here you don't have to guess is x or y independent or dependent. Here we're told specifically the one inside of the function is your independent variable. And we know symbolically, let's say we have the function f of x equals something like 3x minus 4. If I want f of 2, all that really means is we're just plugging 2 in for x. Right? So f of 2 is equal to 2. And that implies to us that the ordered pair 2, 2 is a solution to f of x equals 3x minus 4. Right? That satisfies that equation. Everybody's okay with that? Again, these things should be relatively straightforward and pretty easy. Mostly all review, I'm hoping, or at least sounding familiar as we go. That closes section 1. I know, it's a tough day. Section 2 is about domains and ranges. So again, domain was the set of the x coordinates for your set of ordered pairs, and the range is your set of y coordinates. One way to describe domains and ranges, since domains and ranges are sets, one way we can describe a set is with something called an interval notation. Interval notations are good when sets are continuous. Otherwise, if the sets are discrete, like there's gaps in between the values, you'd want to use your normal set notation. But for the most part, in your high school class, the sets you deal with are kind of continuous. They're connected together. So let's just talk about how to write interval notation. So all interval notations start with a lower bound and then end with the upper bound. And then they're either going to have a bracket or a parenthesis at the start or end, depending on the type of inclusion you have. So if that lower bound is a member of the set you're describing, then we use a bracket. If it's not a member of the set, we use a parenthesis. Oftentimes we'll start with an inequality and then translate that into an interval. So again, inclusion for an inequality means you have a greater than or equal to or less than or equal to. Everybody's okay there? Okay. Did you guys use interval notation last year in Algebra 2? I know some of you did because I taught some of you, but some of you I don't recognize. So I'm thinking that either your mask was very high last year and I didn't even remember this much of your face, or you're in Miss Morgan's class? Okay. So let's just do a couple of examples. So let's say we have x is less than or equal to 2. So when we say x is less than or equal to 2, we mean like 1, 0, -1, and then all the decimals in between all those numbers, right? So like 1.01 and -2.65321, you know, all the way down, right? Okay. So what's the lower bound on this? What's the lowest number? Or what number is smaller than everything else involved in this set? It's maybe not a number. -infinity. Yeah, very good, right? Hello, little stylus. There we go. Okay. And the upper bound here is 2. Right, the biggest number involved in the set, or the number that's, you know, bigger or equal to everything in the set. Okay, the infinities always get a parenthesis, so I don't even have to think too hard about that. And 2 is clearly included in this set because you have a less than or equal to 2, so we get a bracket on that end. And then I'm going to ask that we are a little bit more specific and write that x is a member of that set. So that's like the letter, capital letter E, but it's curvy instead of like has corners like the E normally does. You just kind of curve the corners out. But that's just the symbol that says that, you know, for a member of the set. Probably weren't picky about that in your Algebra 2 class. Interval was probably good enough. We'll be a little bit pickier about some of these notation things as we go on. Mostly because we don't want to bombard you all at once with a new notation, all the little intricacies of it. Let's, you know, take some steps as we go. Everybody's okay with that, though? So far, so good? What if we have -5 is less than y that's less than or equal to 10? The lower bound here is -5. Good. The upper bound is 10. Should the -5 get a parenthesis or a bracket? The -5 should get a parenthesis because -5 is less than y. -5 is not a member of that, does not satisfy that inequality, right? Because -5 isn't less than -5. Remember, the parenthesis is not included. So the 10 then gets a bracket. And again, we want to write like y is a member. Easy to kind of get those parenthesis and bracket confused. Let's try to make sure we get that all straightened out here today. We don't want that to be like a consistent like oopsie-daisy here going forward. So again, parenthesis is for strict inequalities, less thans, greater thans. Bracket is for the or equal inequalities. Let's do one more and then we'll move on to talking about domains and ranges. So this one's a little bit different because this is an OR inequality, but that doesn't really make it any harder. All we'll do is we'll just treat each of these two inequalities separate as their own separate interval, and then we'll connect them together with a symbol. And if you don't remember the symbol, I'll show that to you in a moment. So we'll just start with the first one. A is less than -2. So we're talking about like -3, -4, -5, on down. The lower bound on that is -infinity. Very good. And the upper bound is -2. The infinities always get a parenthesis. The -2 gets a parenthesis. Very good. The OR, we're going to draw the letter U with no tail on it. That's the symbol that means union. So that's the symbol we use for sets when we mean OR. Everybody's okay with that? Do we remember that? Okay, or at least looks familiar. Next one, we have A is greater than or equal to 5. So we have like 5, 6, 7, 8, 9, 10, on up. The lower bound here is 5. The upper bound is infinity. I like to write positive infinity, although it's not wrong if you don't leave the positive. If you leave the positive off, it's fine. I put it on because I like to be, for me, specific or whatever. But parenthesis or bracket for the 5. Bracket. And the infinities always get a parenthesis. And then we should write A as a member of the set. Feeling good? Still okay? Did you do OR inequalities last year with the interval? Okay, good. The next thing we're going to talk about is domains. And I'm going to include or introduce a little bit of a new definition. So we really have two kinds of domains when we talk about things. We have something called an implied domain. And we have something called the relevant domain. So most of the domains that we found in Algebra 2 were these relevant domains. An implied domain is based on the context of the question. So if you just have a purely symbolic question like, what's the domain for the square root of x minus 5? The implied domain is all real numbers. Like could be any, like there's nothing about the problem stated that would preclude any numbers. The relevant domain would be what you actually would have found in your Algebra 2 class based on that. So the relevant domain is always a subset or equal to the implied domain, but it's never bigger. A place where the implied domain might come in is saying the function f of x equals x represents the number of people needed to screw in X light bulbs. There, the implied domain is going to be like the natural numbers, right? So positive whole numbers, because you can't have half of a person or negative a person. Does that make sense? So the implied domain is just like the context of this problem dictates this set of numbers to work from. And then the specific function may further restrict that. Everybody cool? Okay. So let's just run through a couple of examples on some domains. Okay. So the question here is, what operations do we see going on in this function? So I see subtraction, right? Because of the x minus 4. What else do we see? Multiplication, right? We have the 2 times out front. And the square root, right? Which one of these can cause a problem? Not all of them. So if I take any 2 numbers and subtract them, could I ever end up with an issue there? I'll always get an answer, right? If I take 2 numbers and I multiply them, I'll always get an answer, right? If I square root a number, do I always get an answer? No. What's the problem? What? Square root of 0 is 0, right? 0 squared is equal to 0, so the square root of 0 should be 0, right? Yeah, the square roots of negatives, right? You guys remember that? That you don't get a real number when we square root negatives. You get imaginaries. Does that ring a bell? Okay, so that's the place where we're going to be concerned about with our relevant domain, is whatever we're taking the square root of, in this case, it's the x minus 4, has to be non-negative. You guys remember that? Okay. So I can solve that inequality just by adding 4 to both sides. And then I can write it as an interval notation, or write it using the interval notation. So x is greater than or equal to negative 4, so the lower bound is 4, and the upper bound is positive infinity. The infinities always get a parenthesis, and because it's greater than or equal to, the 4 gets a bracket. And we'd say x is a member of the set. Now, how many of you from your Algebra 2 class said, oh, I recognize this as a function in this form, so I know the domain is h to positive infinity, and the range, if a is positive, is k to positive infinity, and negative, a leading coefficient is negative, it's negative infinity up to k. You might have also remembered that. That would have been okay. But that's a lot of stuff to have remembered from a year ago, right? That specific form and everything involved. In general, a little bit easier maybe to think about it in the way that we just did, although not incorrect to have remembered the forms from last year. Did anybody remember that form from last year? Did that ring a bell in their head? I would have been kind of surprised, to be honest with you. That's super specific. So g of x equals 3x over x plus 2. What operations do you see in this function? Perfect. Division, multiplication, and addition, right? We have x plus 2, that's addition, 3x, that's multiplication, and it's written as a fraction, so there's division going on. Of those three operations, which one can cause us a problem? Division. Why can division be a problem? Good, we can't divide by 0. The denominator of our fraction cannot equal 0. So I'll just go ahead and write that way. I can subtract 2 from both sides to get that x is not equal to negative 2. But that's not an inequality, right? So how am I going to write an interval notation for this? I'm going to just turn it into an inequality. This is actually an OR inequality. It's everything less than negative 2 or everything greater than negative 2. Right? Still the same thing as x can't be negative 2, but now we've written it in a form where it's going to be easy to get the interval notation out of it. And that's a trick that probably wouldn't be obvious until you've seen it done, and you're like, oh, that's a good trick. All right. So again, since it's an OR inequality, I just look at the two inequalities separately. X is less than negative 2. The lower bound is negative infinity. The upper bound is negative 2. The infinities always get a parenthesis, and because it's a strict less than, that gets a parenthesis. The OR gives me the union. And then x is greater than negative 2. The lower bound is negative 2. The upper bound is positive infinity. And the negative 2 gets a parenthesis because it's greater than, and the infinities always get parentheses. And we'd say x is a member of that set. Everybody okay there? Again, you might have remembered from your Algebra 2 class last year, you might have recognized that as a simple rational function and know the domain is everything except for where the denominator is equal to 0. We might have allowed you to write like, that the domain is like all real numbers, x not equal to negative 2, right? Were you allowed to do that last year for writing domains like this? I can't remember what I even did, because I always teach the regular and the honors class at the same time. It seems like I can't remember if we did the same thing for both classes or if I did different things for the two, but we're done with that particular notation, just FYI. We're going to use all intervals here. Okay? Okay. Again, the implied domain for both of these last two problems were all real numbers because they were just numeric problems. There's no context to it. Last example for domains. So here we have the function v of s is equal to s, where v of s is the volume of a cube with edge length s. Here we have some additional context to our problem, right? Is this going to change our implied domain? So the domain is going to be the possible values for that edge length. Can the edge length be all real numbers if we're talking about the edge length for a cube? Gotta be, well, I would say non-negative. I would say 0 is okay. Like I'd say a 0 edge length cube is just like a point, but whether you want to, we're not given enough information whether we should count that or not. I'm going to count it. But yeah, so here the implied domain is saying that it's this, right? You can have 0 and up for S. Oops. Let me just squeeze that X as a member of in there. Got carried away and forgot it. Oops-a-daisy. Now let's think about the relevant domain. So that's always going to be a subset. It could be equal or smaller, but can't be bigger. So what are the operations involved with s cubed? Involved with the function. What are the operations? Just cubing, right? You can think about it as multiplication. If you wanted to, that would be fine. Can that get us in trouble? You take a number and cube it. Are you ever going to get undefined? No, right? You take a fraction and cube it. That's fine. And just multiply that number 3 times. You know, you take a positive and you cube it. It's fine. Multiply the number 3 times. You take 0 and cube it. It's still 0. Negative and cube it. Multiply that number 3 times. Like, there's no problems. No matter what kind of number you pick, we can always do that operation. So in this case, the implied domain is also the relevant domain, right? Since there is no further restrictions, because v of s equals x cubed is, doesn't have any problematic operation going on in here. As a reminder from your Algebra 2 class, the things that you encountered, the operations you encountered that could give you a problem. Division, even roots, logarithms, that would probably be the end of it. And I don't think that, I'm trying to remember, but I don't think in the homework set you'll see any logarithms till we actually do the log stuff in second semester and we redo parts of that, because in my experience, that's this topic that usually deserves a second pass for most students, is it's a difficult topic. Is everybody okay with what we just did there? Okay. What if we wanted ranges for these same, we're going to do ranges for these same functions. So the ranges are almost always going to be more difficult than a domain. And the easiest way to be able to deal with ranges is if you're able to identify whether the function is increasing and decreasing, or even where it's increasing and decreasing. If you have something that has parts that are both. So remember that when we say increasing, well, let's just write down the first one here. So these are the same 3 functions we just did. And I did that specifically because I want to be able to use the domains. Oops. I did it again. So if we remember back to our Algebra 2 class, the graph of a square root function either looks something like this, or it might look something like this, right? Everybody's kind of remember that? So the red graph is increasing because as you go to the right, the graph is going up. And we can tell when the graph is going to look like that because we know the leading coefficient should be positive. The blue graph is decreasing, and we should be able to identify a decreasing square root function because the leading coefficient would be negative. So here we can see that this is an increasing function. Everybody's okay there? So in general, if you have a function that's increasing on the interval from a to b, the range over that part would be f of a to f of b with the same inclusion as the domains. So whether the parentheses or bracket were the same, they're just going to be the same on the ranges. Is everybody okay with that idea? Decreasing, they're going to switch. And the inclusion, the bracket or parenthesis, goes with the upper or lower bound from the domain. So you notice here the bracket and parenthesis switched locations, but really the parenthesis stayed with the A and the bracket stayed with the B is really what's going on. So just in general, that's, I think, this is the way that I like to think about ranges if I'm doing this purely algebraically, is just thinking about increasing and decreasing parts. Because then I can evaluate and just, I get a nice picture of what's going on. So, since this is, since f of x is increasing, I know the range is just going to be going from f of 4 which just gives me 0. Everybody okay with why that's 0? I skipped doing the arithmetic, but I think for the honors class that's okay, right? If you're confused, you can always ask and I'll give more details, but sometimes I'll just skip through some trivial calculations. But if you're like, hey, how did you get that? Please holler. And then f of infinity, because that's the upper bound, right? How do I parse that since infinity is not really a number? Well, let's just kind of follow the order of operations. So infinity minus 4, if you have an infinitely sized number and you take 4 away, does it matter? No, still infinity, right? Okay. Take the square root of an infinitely sized number. Well, it gets smaller, but does it really get smaller? It's infinitely big. It's still infinity. Right? And I multiply 2 times infinity. Well, it gets bigger or whatever, but it's already infinitely big. It's still just infinity. So what I have here is that y is 0 to positive infinity. Again, the bracket and the parentheses stayed Since we had a bracket with the 4, we got a bracket with the 0. Since, oops, I'll do that different color. Since we had a bracket with the infinity, when we plugged in infinity, whatever we got back from it, got a bracket. Is everybody okay with that? In general, when dealing with the infinities, with the arithmetics, the only thing you really have to worry about is like infinity times 0. That's 0, not infinity. Or infinity minus infinity, that can be 0. Or if you had like infinity times a negative, that'll be negative infinity. But those are really the only operations on infinities that like get you something that's not infinity. You know what I mean? Okay. The next one was g of x equals 3x over x plus 2. And our domain there was negative infinity to negative 2, and then negative 2 to positive infinity. I don't know why I put a bracket there. That's okay. Okay. So here it's a little bit, again, I'm going to think back to my Algebra 2 class, and I'm going to think about, okay, this is a rational function, right? Because it's got a polynomial on top and a polynomial on bottom. And this is actually a simple rational function because they're both x to the firsts. Everybody's okay with that? So I know that for a simple rational function, it's going to be like what its shape is going to look like. It's going to be like a vertical asymptote where the denominator is equal to 0. And then it's going to have a horizontal asymptote. And since there's x the first on top and bottom, that horizontal asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator. So 3 divided by 1. So it'll look something like that'll be kind of where the vertical and horizontal asymptotes are. And then the arms of this graph are going to be like two hyperbolas. In this case, since the leading coefficient is positive in the numerator and denominator, the graph will look like this. If one of them was negative, the arms would be there. They're always going to be like kitty corner from each other, though, in a simple rational function. Is everybody okay there? So the big takeaway here is that this piece is decreasing and this piece is increasing. That's the part that I care about. The rest of it was just to get an idea of where they were increasing or decreasing at. Everybody's so far so good? Okay. So if I do this now, I'm going to do f of the upper bound to get the lower bound for my range. So negative 6 over 0, which is undefined. But that's okay, because undefined really just means either positive or negative infinity here, right? Since this is a lower bound that I'm finding, I know that the infinity has to be negative, because you can't have the lower bound of something be positive infinity, because the lower has to be smaller than everything else in your set. Is everybody okay with that? If I do f of infinity, well, infinity plus 2 doesn't matter. So I can just replace that with infinity on the bottom. But here's a question. 3 times infinity divided by infinity. That's 3. Okay with that? So we have negative infinity to 3. And since everything was a parenthesis in my domain, I'm going to get parentheses in my range. And then I'll do the same thing over here. So this is increasing. So I have negative 2. I'm sorry. Negative 2 to, oh, no. Sorry. Wait, hold on. Oh, what am I doing here? How come nobody screamed bloody murder at me? Does that look decreasing to you? Or increasing to you over here? That's decreasing also. Great balls of fire. How come you guys didn't yell at me like, that don't look increasing to me? If it looks like I make a mistake, please holler at me. Or something I do, you're like, are you sure? Totally fine if to say, are you sure? And for me to still be right, does it make you a jerk or something for going, are you sure? Totally happy to recheck it. Okay? You guys are all, quite capable. So if you think something's up, it's very possible that I just made a mistake. It's okay. I don't mind being corrected. Anyways, so since it's decreasing, we flip. And I'm not going to bother to write out the work that time for f of infinity since it's the same thing. And here, since f of negative 2 is an upper bound, I know I'm getting a positive infinity for that. So, here we go. How you feeling? Still doing okay? This was a little bit more challenging, I assume. Alyssa?
How did you get the positive at the bottom?
Okay. So because this was an upper bound, it's going to be a positive infinity. Up here, when we found the lower bound, that's how I knew it was going to be a negative infinity.
Okay.
Has nothing to do with the sign on the 6. Is that okay?
Yeah.
So over 0 just tells you infinity. Positive or negative, you can't tell other than the context of what it is you're doing. So if you're building an upper bound, and you get an infinity, it has to be positive because it has to be bigger than everything else, right? So like if I had written 3 comma negative infinity, this is nonsense, right? It'd be saying like, 3 is less than y, which is less than negative infinity. Well, there's no numbers that are between 3 and negative infinity. You know what I mean?
Yep.
So that's how you can tell the signs. It's just kind of common sensing it out. Does that?
Yeah.
Okay. Because that's subtle. That's not like, wouldn't be super clear as to like what to do with that. Probably had you not been told like, that's how you can tell whether it should be positive or negative infinity. You know what I mean?
Yep.
Cool. And they're perfectly happy to clarify stuff like that again, like absolutely important. If you're not getting it, I guarantee you that somebody else in the room is also missing it and you're not the only one. So speak up for the good of yourself and the quiet person that's, no matter how they're doing, is never going to say anything. All right. We'll do one more section because it's largely just some vocabulary and not really any computation at all. Because we have 25 minutes and we'll just be done here. I don't think this changes the length of the homework assignment because I don't think this comes in. All right, section 3 is about continuity. So basically our definition for continuity is a graph that you can draw without having to pick up your pencil is continuous. there are three types of discontinuity. Two of which you've seen already. So one, well, maybe have seen, I don't know. If you're in my class, we've seen this removable discontinuity. Miss Morgan, did you guys do this? Morganites? You would have done it with the rational, with the general rational functions when you did that. If you didn't, that's okay. It doesn't really put you at a significant disadvantage. So an example of what a removable discontinuity might look like is something like this. So the open circle there is kind of akin to, like when you drew x is greater than 2 on the number line. You put that open circle at 2 and then drew your arrow to the right to indicate that 2 wasn't included. You guys remember that way back in like Algebra 1 or even pre-algebra? Same notion or notation we're using here on the graph. So the open circle is saying that point is missing on our parabola. And instead of being where I'd expect it to be, it's like located over here, right? So all the x values are defined, but you can't draw that parabola without picking up your pencil and putting the dot down there and then coming back. Is that okay? It's almost like you've removed one part of the graph and put it somewhere else. Hence, removable discontinuity. The other one is a jump discontinuity. This I don't think anybody would have seen. And just FYI on a removable discontinuity, this point may or may not be there. It doesn't need to be there. Okay? So if that point is also gone, if it just has a hole, that's still a removable discontinuity. Do you guys get what I mean? Okay. So a jump discontinuity, you'd have something like this, where the graph just like jumps up and it looks like there's some stuff missing in between it. One thing to be careful about here on the jump discontinuities is that one end must be open and one end must be closed. Well, no, let me rephrase that. They both can't be closed. Why not? Failed the vertical line test. Wouldn't be a function anymore if they're both closed because they're occupying the same x value. One open, one closed is fine. Both open is fine. Both closed, no bueno. Just as a heads up. And then the last kind is like an infinite discontinuity. And that's the one that we'd be most familiar with. Because this is really just a vertical asymptote. Oops, that's getting a little messy for my light taste. So an infinite discontinuity is really just a vertical asymptote. So far, so good? Still doing okay? Okay, still have lots of time. So let's do a couple of examples and then we'll get out of Dodge here. So let's just work on identifying some of these discontinuities. So our first one, f of x equals 2 over x squared minus 4. So this one is a general rational function. Should have recognized that from the Algebra 2 class. So if we factor everything that we can, x minus 4 is a difference of 2 squares. That factors to x plus 2x minus 2. Doesn't matter the order which you write those. So then I check to see if anything can reduce. Nothing can. So I can find my vertical asymptotes by setting the denominator equal to 0. And then using the zero product property, I can set each of those factors equal to 0 and solve them separately. So the vertical asymptotes are the same as the infinite discontinuities. So that's all we can have there. Or if we asked you where it was continuous, I guess, or we could say it's continuous from negative infinity to negative 2, and then negative 2 to positive 2, and then 2 to positive infinity, right? Everywhere around those infinite discontinuities. So coming up to negative 2, in between negative 2 and positive 2, whatever it does in there, and then after positive 2. Everybody okay with that idea? You can picture this in your head, I hope. Not specifically what it looks like, but like, does something get an asymptote, so the continuity ends at the asymptote. It does some more stuff, you get an asymptote, continuity ends there, starts over again, and goes forever after that. So we have like 3 continuous chunks. Is that okay? Does that make sense when I describe it that way? Okay. Our next one is this. Again, which we recognize hopefully as a general rational function from last year. I'd want to start by factoring. So the numerator factors to x plus 3 over x minus 2. The denominator is already prime, so that can stay how it is. Now I check to see if I can reduce, and there is reducing that I can do here, right? The x plus 3's can reduce, leaving us with x minus 2, where x cannot be negative 3. Morganites, are we good with why I have the x cannot be negative 3 at the end? Okay. Again, I'm always, we taught different classes. I don't know, sometimes we emphasize different stuff. So this is your removable discontinuity. So x equals negative 3 is my removable discontinuity. Or if we're asking where it's continuous, everything up to negative 3 and then everything after negative 3. Is everybody okay with that idea? So just like it's the same, it's like we're asking a different question, but it's the same information, right? If I tell you where it's discontinuous at, then everywhere else it's continuous. If I tell you where it's continuous at, the place where it's not, or it's discontinuous. I can't tell the kind of discontinuity without the equation, but if you just tell me, where it's continuous at, I know that, there has to be some kind of discontinuity there. What if you have something like this, that's just a polynomial. This is the best case scenario. Is there any way I can get something undefined out of here? No, right? Because all we're doing is adding, subtracting, and multiplying, basically. Can never make something undefined by doing that. So this is just everywhere continuous. Are we okay with why I was able to determine that just by looking at the equation? In general, I'll tell you this, all polynomials are everywhere continuous. As a general rule, all polynomials are everywhere continuous, which is really nice, right? Notice that we didn't do any piecewise one or any jump discontinuity ones, mostly because the easiest way to get one is using something called a piecewise function, which is kind of beyond the scope of what we had done. But a piecewise function, the general idea here is the notation is going to look like this. We'll say f of x equals, and then it'll say like so you describe it in two pieces based on like, okay, for one part of the domain, we're going to do this function, or this, you're going to use this rule. And then for another part of the domain, we're going to do a different rule. So like, oh, this is a bad example. Let me do this. Make that a 3. Before, if I didn't do that, they were going to be connected. I didn't want them connected. So if we do this, oh, and one of these should be, it's fine, they're both inequalities. So if I do the top one, I have at 0, we have an open circle, and then we're going to be doing that something, right? Everybody's okay with that? If I do the bottom one, I have an open circle at 3, and then we'll have, oh no, we wouldn't have, we have a negative slope, so we'd be coming in like that, right? So there's a jump discontinuity. You really kind of need a piecewise function to define a jump discontinuity. And I don't think that we really cover those in anybody's Algebra 2 course. But that's an example of what like a jump discontinuity or a piecewise function would look like and how it ends up creating a jump discontinuity. Which in the real world, piecewise functions make a lot of sense. You imagine like, hey, if some conditions are like this, it behaves this way, but as soon as we get too much of something, it behaves somewhere different. But then if we get way too much, it does something different even then, or you can get like a piecewise function would make a lot of sense, right? We'll stop here. I think that's way enough to do for today. Looking at your homeworks, oops. I think I just need you to do 1 through 12. Yeah. That seems fine to me.
My link is not syncing.